Okay, so today what I'll do is I'll go over material that's been posted, especially on Project Checkpoint 1. That was announced last time, but you probably haven't seen it. And in addition to Project Checkpoint, I have also been posting these so-called homework, but really you're not required to do. That doesn't mean you shouldn't do them. And you shouldn't let the length scare you, because each one is supposed to be very simple, okay? And operating system is one of those things where if you're missing one thing, you don't really understand the whole thing, because it's about connecting things together. It's right in the middle between hardware and software and between programs. So you really got to know all the concepts. And so why I took extra time, I didn't have to do this. I took extra time to ask detailed questions based on the slides, because if you don't understand even these basic questions, then I think you may have trouble understanding slides. So when you review, be sure you really are able to answer. You don't have to write these things down, but do you even know what these things mean, right? So, I think it's really important that if you don't understand something, go back and find out what you don't understand and ask questions. I think there were a lot of activities in the first 3 weeks. But after 3 weeks, I think people somehow stopped asking questions. Either they gave up. Please don't give up. This is important. And most of all, if you're looking for, if you're looking to do well on your exams, I take questions straight out of these. Okay, maybe I combine 2 or 3 of them. So this is your source for review. Okay. So anyway, what I'll do is I'll first go over the project checkpoint. Basically, it's another way to make sure you know what you're doing, and I provide a lot of guidance. Basically, if you understand what I'm saying, you should be able to just build it, express it in C and assembly, okay? It's really that, because I have done the work. I know how it works. I run into problems. I tell you the problems I ran into, so you don't have to struggle with most of these things. And going through the process really gives you a good feel for what it takes to do a threads package. Do you have a question? No, follow the direction, please, and I'll go over it. Follow directions. You have to follow directions. You could do whatever you want, but in the end, if you don't follow directions, you'll have a hard time. I tell you where to write in C, where to write in assembly. Yeah, follow the directions. Yeah. So please really read this very carefully. Make sure you understand everything, because I think what I do is I wrote it once, ran it, tested very thoroughly, then I went back and basically just expressed what I did in English. So if you follow my steps, and I give you rationale as well. You do have some options to do better in your implementation. There are ways to optimize things. You can do things a little differently, as long as it's supporting the required functionality. Okay. So, as a project checkpoint, all that means is that you better be able to reach this milestone at some point. Preferably in a week, maybe 2 weeks, it's okay. I'll let you take your time. You may have midterms in other courses coming up. You may have other things. So I'm not going to hold strict deadlines for you. And in fact, you're not required to turn in anything. But that doesn't mean you shouldn't be doing this. Because if you don't do this, you can't finish the rest of your assignment. This is critical. Every step is critical. And it builds on top of the previous one. Okay, and so what that means is really treat it as if it was a real assignment. But for grading purpose, yes, you can check, go and ask the TA, make an appointment, whatever, get them checked, and if you have questions, get them done. And then once you get past this point, this is about 20% of your project grade, which I think is total of programming is about 35 or 30 to 35%. Project, that's part of your grade. So if you don't do this, you can't pass the course. You have to. It's mandatory. And I think it's important because you really need that experience. If you just read on paper, you don't get that feel. It's very different. After having been through this, you get a much, much better sense what it takes. okay? And that's really that nice mix between assembly and C. So yes, you will have to write in both, most of the time in C, but you need to know what that assembly looks like when you translate it, okay? And the compiler does the translation for you. Is that what you expect? Is there something that's different and maybe you have to do some fixes in there? Sure, you can write everything in assembly and not rely on a single line of C. I don't recommend doing that. It's kind of a pain, but it's certainly doable. I think most operating system, modern operating systems assume you at least program it with C, right? So being able to support at least that function call abstraction is important. Anyway, and so this is really in the end of the quarter, you'll be graded by in person. Okay, every single person has to be signing up with a TA for a grading slot, and you have to turn in something. And so if you don't do the write-up here, that's okay. You do a write-up for a later one, and it's whichever the last write-up you do, that's what you get graded on. Okay? So if you don't bother with the write-up here, okay, fine. You think you're confident and can do the remaining ones, fine. We're graded by the last one, and then if you pass a later one, we assume the previous ones are all done, right? So that save you time, save us time, but really you got to be honest with yourself and do everything in between. This is what it takes. Okay, so there are you saw what I explained on the slides. There are 3 files in the source file. One is testcoop.c. That's the startup code, and it sets up the producer-consumer example, right? So that's a single buffer, producer-consumer. Now there's cooperative.c, that's the threads package, and cooperative.h. So anyone who wants to use the cooperative threads package would need to link with a .c file, compile into .rel, you probably remember that, right? And then the .h is the header. So when you call any API, that's all defined in the .h. You should know this by now. And then you should try to really use makefile. You'll have much easier time than having to type in those SDCC commands by yourself. Makefile is really this thing all computer science majors should know. It tracks the dependencies between your source and object file. So if you change any source, then it knows which ones need to be recompiled, which ones don't. And it does the linking for you. So all you type is make. That's it. And so if nothing has been changed, it doesn't do anything. It's done. If you change one thing, it compiles only the necessary files. So in fact, I even wrote this for you. You just have to set up your environment to run make. Most Cygwin or most Unix-like environments, Linux, Mac OS, already should have these tools built in. Running on Windows, well, good luck. Install Cygwin or install one of our virtual machine images. I think that's been posted too. Certainly you could run Windows 10 PowerShell, but that kind of sucks. I still recommend a Unix-like environment. And you can certainly set up whichever that supports. Make, this is such an old time program from very earliest day of Unix. You got to know. TypeScript is really just a way to record the input and output for your shell session. And so that way you can replay and then see what's going on. And that helps TA as well when you ask questions. And so now, so the purpose of this first checkpoint, as I said last time, is to implement a cooperative threads package plus your test case, in which case, producer consumer with a single shared buffer, right? That you should know very well by now. And so what does the cooperative.h look like? Well, type dev char thread ID. We explained that already, right? So that's the type. It's better to do this so that your program is more readable than just do char as the return value for char. No, it's really not meant to be a char. It's just a byte. Now, function pointer type, right? So you should know this. So function pointer is the type, name of the type, which is a pointer to a function. Takes void as its argument, returns void as its function, right? So Now, the API thread create, thread yield, thread exit. These are three functions with a C calling interface. Now, just because you have a C calling interface doesn't mean the function itself is written in C. It just has to provide the header, right, in the .h. But once you have the header, you really don't care if it's written in C or assembly. Everything can be written in assembly, really. So, but you could write big chunk of it in C. There's going to be a little bit you do assembly. We do inline assembly. That's okay. That way, you limit the ugliness in the little chunks of code, but you can still reason about it mostly in C. That's nicer. Okay, so if you are adventurous enough to write this all in assembly, great, more power to you. But your code is less portable. Okay. Anyway, so thread create. That's somewhat similar to the POSIX API, but POSIX API, as you know, has lots and lots of other arguments, right? Because it wants to support functions that can take arguments as well. So it takes a pointer to any struct. The function itself, the callee, has to know how to cast that pointer back to its struct pointer. Here we just say, nah, let's not take any arguments. So very simple, single argument, which is a function pointer, okay, to thread create. And what it means is you create a thread and then have it start running that function. That's all. You don't need a separate .start like you do in Python. And whoever calls it gets a chance to store or manage or save that thread ID, but a lot of times just throw it away. Doesn't matter. Okay. Yield. Yes, this one. So as this thread is running, if it wants to be nice to others, say I'm gonna yield here because I'm waiting on UART. I'm waiting for the buffer to be filled or something, right? Or buffer to be consumed. I have nothing else to do a yield. That's nice, right? So then it doesn't take any argument. It doesn't return anything, right? But if you want to implement Python style, then you can have it return some value or you can pass some value to it. Let's not do that. Now, thread exit, so for now, we don't do anything with it. We don't call it, but we just do a placeholder. Okay. Now, what you need to do is the memory assignment, because this is such a limited memory architecture. It's okay. When you should remember, we're making use of the register banks, right? So R0 to R7, if bank 0 is selected, then gets mapped to address 0 to 7. Bank 1 is selected, gets mapped to memory address A to F. Bank 2 is 10 to 17 hex. And bank 3 is 18 to 1F, right? Each one is 8. And then how do you select the bank? Again, PSW bits 4 to 3, okay? And so there's name RS0 or RS0, RS1. These are bit address names, but you can also just set the PSW. And you should know how to change only a few bits in a register. You should know how to do that, right? So if you want to change only bits 3 and 4 and keep the remaining bits, what do? Well, you read out those all the bits, you mask out bits 3 and 4, you OR in the bits you want, right? So you should know that. And that should make perfect sense to all you guys because you'll pass the prerequisite quizzes, and so you should be very comfortable doing bit level operation. Or if you want, do it in assembly. That's fine too. Now, and we did the stack assignment. 40 to 4F hex is the stack address range for thread 0. 50 to 5F for stack 1. 60 to 6F for stack 2. 70 to 7F for stack 3 used by thread 3. So everybody should be okay up to this point, right? If you don't, you're in trouble. You gotta really know this. And you can declare your own memory usage between hex address 20 to 3F. Okay. Now, first, look for the code, and that's testcoop.c. You say, but I haven't written cooperative.c. How can I write test? Well, you could. In fact, you should just write the producer and consumer example. So I give you the template, and look for the triple @ sign, like here, right? Because that is a way to show, well, here is a comment you should read and do something about. Okay, so replace the comment or add to the comment your code according to the instructions. So here is where you would declare your global variables for the shared buffer, right? And then between the producer consumer. And I even give you some hints on how to do that. So, well, a lot of times when you declare a variable in C, what do? You just say int x, char y, something, right? But then how do you know where the address goes? You don't. The compiler and linker decide, right? Compiler just says, here's some address, this is, well, here's a name, and this is how big it should be. But where does it go? Well, the linker decides, right? Because depends on what else is in there, it just starts piling things up and then accumulates the address and then figures out, I'm going to put X, I'm going to put Y here. So the linker is the one that assigns the addresses. But if you add another variable or delete another variable, what happens? Well, that address shifts, okay? And so each time you recompile, that variable X is going to go to a different address, which is probably not a good idea because you don't want the compiler to do things. We're doing all the assignments here, and you could try to declare the stack as an array. You could do all these, but SDCC fortunately provides a way to say, I know what I'm doing, let me assign this variable to this address. So it even needs, lets you say which bank. So _data says in IRAM, this is another one of those special keywords just for SDCC. And then at what? At hex address 30. This is one of those addresses we can use, okay, available for us to use. And then the type. So basically everything before the type, that is extra information you give to this compiler and say, I know what I'm doing, put this variable in this bank at this address. Okay, then linker will say, okay, you know what you're doing, I'm going to respect that. And so it's not going to assign something else on there, okay? And so it'll find other free memory to this. And otherwise, the type and var, this is exactly like your conventional C. You can do int x, char y, and things like that, okay? So that's how you would declare your variables at and here, this is a byte address, okay? And you know what variable you have to declare. It's a single byte shared buffer, not very hard, right? And also a bit or a byte to indicate if it's empty or full, right? A Boolean. If you want to do a bit variable, you could. You would just do like _bit, right? And you can read SCCC on that. And all the user assignable bits would go into address 20 to 2F in the byte address range. But for now, you can just use byte. Unless you really want to squeeze and optimize memory, then we can use bits to save some space. Okay, then you have a producer here. Producer, what does it have to do? Well, I even write the documentation for you. And then producer basically runs, it's supposed to run as its own thread, right? So what does it do? Producer, in this case, needs to generate that letter, ASCII letter A through Z, and then start over again, right? So, and you've seen the general purpose version. A lot of times we use a static char, right? And then initialize it to something. And then, now, when you do static, you can also do the same trick as here. Why? Because static is a lot like a global variable, except its visibility is within the function only, okay? And declaring as a static local is nice because then nobody else gets to modify it. And in this case, like which character you're about to generate next, you probably don't want any other function to modify it, right? So then you can declare a static local, but you can specify its address at. Just make sure it has its own address space, and you're allocating your own memory that way. Okay, and then again enters an infinite loop. In C, an infinite loop is just while 1, right? Or you could do while anything that's not a 0. Then what do you have to do? Wait for the buffer to become available, write new data into the buffer. Okay. I mean, you could probably copy the code from my slides a few lectures ago. Most of it is pretty much the same. So producer part is really not that hard. Okay, but it does have to make use of shared memory. Now, what about consumer? Well, consumer part, in this case, I require you to use UART because as a user, you can type characters into the UART window, or you can write out to the UART, right? So to write out, you would say write to sbuff, right? And if you write to sbuff, it shows up on the UART window. So that's what I'd like you to do. But you can't just keep writing it. You have to see, are you busy? If you're ready to accept, I write. If not, then I clear, right? So there's a initialization. Well, there's two parts to it. One is to initialize the UART, and I suppose you could do it somewhere else, or you could do it inside consumer. Either way, and then it needs to do checking the UART, and you could do either interrupt version if you're adventurous enough, or for now I'll just do the serial or the polling version. That's easier because it's probably not doing much else anyway. Now, when you poll, you could also yield in the meantime. Poll a little bit. If nothing, yield. That's a nicer way, but you do more context switch that way. Or you could just hog the CPU, poll until you could write and do, right? So anyway, so there's two loops here. One is to wait for new data from producer, and the other is write data to TX, right, UART. So there's going to be two loops here. Wait for new data from producer, and so you better do the yield when you wait for producer to produce something. Otherwise, what happens? The consumer hogs the CPU. Give me data, but then producer doesn't get to run at all, right? Then so unless you yield, then okay, producer can can produce the next data. Then you can get out of that loop and then write to UART. Now, if you don't yield in UART, what's going to happen? Well, it's probably going to work because you just wait longer before you. I mean, eventually the UART is going to be ready, and so you can write to UART, right? So it's your call what you like to do, and then poll for TX to finish its transmission of the previous byte, if at all. And then when you could write to it, and then so no, you clear the flag and write, right? So I have sample code from previous lectures, so you can take a look. And so really, all I ask you to do is take the consumer. So instead of printf to screen, you do a write to UART and you poll. So that shouldn't be that difficult, right? Now main. Okay, so what does main have to do? So main initializes globals. Sets up producer, consumer, and so then it doesn't return, okay? And as I said earlier, you have the option of running two threads, one producer, one consumer, but main wouldn't have anything to do, so it should just enter an infinite loop. Or you could set up you could run a thread for either producer or consumer, and main itself calls the other one, right? It reuses this thread, okay? So that's really what it takes. And the rest is really just stuff that you include. STCCG as init startup, and then this is how you do inline assembly, right? And in case you haven't seen or you've seen it and forgot, in STCC and in most other language you could do double underscore ASM and then double underscore end ASM. And in between, you use the assembly code, and it's slightly different from the Intel assembly. This is more the portable version, more GNU-like portable assembly, in the sense that they use more C-like syntax. So in hex number, you don't have to do like 10H. You do the 0x10 for hex, right? And then it has a bunch of other directives that Intel assembly doesn't have. So it has the dot, I don't know, text dot bisect by something, for different segments. But you shouldn't need to worry about that because we have a much more restricted architecture. And the rest you just include so that you don't accidentally call some library function you didn't write, okay? Because we don't really need those. Okay, so that should be the content of your test co-op.c. So that is the test case, and that's where main is defined, because the user code is the one that defines main, right? And then, but by itself it wouldn't run because you really need to call the API, and the API doesn't exist. Okay. I mean, I suppose we could give you the .rel file just to link for you to test your test co-op.c. And so that way you can link with our rel file and then just to see if that works. But you should make sure you assign the addresses consistently. Anyway, cooperative.c, that's the implementation for the threads package. So what do you have to do? Well, first you have to include 8051.h, and that should be in the include path of your SDCC setup. So you already had a couple weeks to try this. It should work by now. And then include cooperative.h. So now we're in the .c file. We saw the .h, right? So here, what do you have to do? Similarly, you declare the globals for use by the threads package. So you need to do. What? Let me go over it, and if you want to ask a question, please raise your hand. Okay. So here, this is the cooperative.c file. And again, if you see triple @ signs, that means that's where I want you to write some code. And what does the code have to do? Well, read the comments. Okay. Declare the static global. Now, static global in the case of a C file means its visibility is only within that C file. Okay. Similar to if you do static local in a function, then its visibility is in that function only. But it otherwise acts a lot like a global. So reason for doing static global is we only the functions in this .c file are supposed to use it, right? So you do similarly data at address type name. That's the syntax for manually assigning address, because the threads package does need to track a number of variables. What are they? Well, one could be the current thread ID. You need to know which thread you're currently running, right? You probably need a mask or bitmap to say which thread IDs are active, right? So a compact way is to just use a bit to indicate which to correspond to each thread. So if it's that thread ID is active, then you have one bit. That thread ID is not active. That corresponding bit would be 0. And do you need a count for how many threads are currently active? Maybe, maybe not. Probably not necessary in this case anyway. But later, if you do a more sophisticated scheduler, perhaps. And other schedulers may have additional state to track. What are they? Could be aging, could be priority, could be any number of those things. Okay, so there could be additional state. I'm just telling you that the whole point here is it may need additional state. We're just saying that's where those additional variables would go. Now, then you need to define some macros, and I talked about these macros for inline assembly. And what does it have to do? Well, one is for saving state, or another way of saying is saving context. The other is to restore. So one is the inverse operation or the other. To save, you put ACC, B, data pointers, or DPH, DPL, and PSW, right? And then now SP has to be saved. And I did tell you a couple options. One is to declare an array of 4 bytes. Or another way is you may shrink your stack slightly by 1 byte, and then you stick it at the bottom of the stack. That's another way. Okay, so that way you don't take up space in your 20 to 3F range. And so save the SP into the stack pointer array. I mean, you could use that to begin with, and later you can optimize it. And so this should be written in inline assembly. Okay, and now saving SP, you could write it in C or assembly, that's fine. But pushing and popping, you really have to do this in assembly. If you can figure out a way to do it in C, okay, great, but it's probably not going to work as you expect, and you should know why. Because when you C compiler generates code, it actually makes use of some of the same registers you're trying to save, and that's going to be bad news because while you're saving things, you just mess up the registers, and then they're no longer valid, right? So, okay, so save state macro looks like this. So it define save state, doesn't take any macro parameters, and in macros, if you have to go to a new line or multiple lines, you have to do a backslash. Remember that, right? So just like other extended thing or even strings work this way too. So again, ASM and then your assembly code here. Now your assembly code looks, it should be in the SDCC assembly syntax rather than the Intel syntax, but minor difference. And you can get an idea by looking at the .asm file, okay? So, and it's really, what does it have to do? Exactly this, push, ACC, push, B, push, DPL, DPH, PS. Really, that's, and then finally, it has to save the stack pointer, okay? And then the restore state, exact opposite, even in ordering, right? So you first have to restore the stack pointer of the current thread. Once you can do it, then you can pop. Otherwise, you're still pointing at the wrong stack, right? So you really need to know what to do here. Don't copy anybody else's code. If you don't know why, you'll have trouble understanding how the rest of this thing works. So this is fundamental, okay? Now, we talked about this before, right? Because Bootstrap has to start main, we just do extern void main, and that's all you do, nothing else. And no brace, and then content of main. No, main is declared in the other file, the testco.op.c, okay? Now, Bootstrap, okay, so what does it have to do? So it has to initialize data structures for threads. And in fact, on the slides, I also show you. So there's a bit mask, thread ID, right? And so initially all empty. If you create one thread, then you put a 1 bit there, right? And then you can, you couldn't move the stack pointer elsewhere, or you could just use the power on stack, which is empty at address 7, and it starts pushing its 8 and up, right? It really doesn't matter here, but it's really up to you, because pretty soon after you use it, stack gets wiped out anyway. Okay. So create a thread for main, and so after the current thread is set to the ID, you do a restore state to start running main. Okay, so and then create thread. This is really the function that sets up the context. So go back to the slides from last time. You really have to have that mental picture. Where are you running now? Which stack are you running? Which stack are you setting up? So first, what does thread create have to do? Well, it has to check, are we, do we have any more threads to create? If you already have 4 threads, sorry, we don't have any more space, right? So you shouldn't create more threads if it's already exceeding, it's already at the max. So now how do you do that? Well, you could have a variable for thread count, but that's probably not necessary. You already have thread bitmap, right? So you can see if all the bits are set. So that saves you 1 variable. Now, if we can create a thread, okay, you gotta then say what ID it is. Again, you can go through the bit mask and see which bit corresponding to the thread ID is 0. If so, let's reserve it, right? Grab that ID and then set the bit so that nobody else can claim that ID. Then, what do? Well, okay, well, one is update the bit mask, as I just said. If you have a thread count, increment it. If not, then you just leave it. And then calculate the starting stack location for the thread. Well, easy, because thread 0 starts at 40, thread 2 starts at 50, thread 6 starts at 2 starts at 60, thread 3 starts at 70, all hex, right? So you should know the initial position. You don't even need a table for that. You can just do some bit shifting and get that. And then save the current stack pointer in a temporary, and then set SP to starting location, and then push the return address, right? And so return address for the function pointer, right? So initially we pass main, later we pass producer, later we pass consumer, and so forth. So that's the function pointer, that's 2 bytes, right? So we push the return address first. Why? Because after restoring the registers, all you have is the return address. Then you can return to it to start running it. Okay? So you should be very, very clear. There should be absolutely no question up to this point. Otherwise, you can't do this. Right? So so the bottom of the stack should be the return address for the thread you want to start. Then, well, you should also know dptr is dpl concatenated with dph. So in which order do you push? Do you push dpl first or do you push dph first? Well, it depends on the endian, right? Because Intel is a little endian architecture. That means which first? And stack grows up. So anybody? So stack increases when you push. Well, you gotta know this. If you don't, then no point for me to continue. Do you push DPL or DPH first? DPL first, correct. Because you're at the lower address, push the lower address first. Little endian byte order, then push DPH, right? That makes sense. Now, we want to initialize the register 0, so we can push 0 value. And it's important really for PSW. Why? Because for ACC, B, DPL, DPH, initially, they don't contain anything valid anyway. But for PSW, it's important you initialize to 0. Why? Because for the register bank select, the middle 2 bits are the bank select. So you got to pay attention to the initial value for PSW. Everything else really doesn't matter as much, but PSW it's critical, right? And so, but it's nice to initialize them to 0. And can you do push #0? No, because push requires a direct address. So what do you have to do? You then pick a memory location, put a 0 in it, and then you keep pushing that memory location, right? So that's the way you do it. And then you need to push PSW. And that should be the last thing you push, first thing you restore. Why? Because first thing you want to do is make sure the register banks are set correctly, right? Then you can make safe use of the registers. So that's why PSW should be the first, or should be the last to be pushed, first one to be popped, okay? And PSW, quick review, is an 8-bit register, and each bit has a name. CYAC, so that's what auxiliary carry, F0 user flag, RS1 and RS0. Remember RS1, RS0? Those are the register bank select bits. Okay, so you then need to know which bank to select for that thread. So if you encode your thread ID in binary, what you can do is take the thread ID, shift over to the left by 3 bits. Then put those bits in there. Okay. Then all the other bits can be initialized to 0, except for RS1 and RS0. That really should be the same as your thread ID. Okay. And then thread 0 uses bank 0, thread 1 uses bank 1, and so forth. So that takes care of the bank selection. So I even give you the bit pattern if you want. So for thread 0, PSW value should be all zeros. Thread 1, it should be 0, 0, 0, 0, 1, 0, 0, 0. Thread 2, 0, 0, 1, 0, 0, 0, 0, right? 0, 0, 0, 1, 0, 0, 0, 0, 0. Anyway, so basically the whole point is the middle 2 bits, right? The middle 2 bits. That's 0, that's 1, and then 1, 0 is 2, and 1, 1 is 3. Okay? So far so good? You gotta know this. Then the current stack pointer, because it's done a lot of pushing, popping, right? And then save that. So then somebody who's ready to jump to it can read that stack pointer, restore, have the correct stack, and then run from there. Okay? They would restore the pointer, pop, 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 until return address, do a return, they started running. Okay? And that's the same mechanism used whether they do a yield to be restored, or you do the initial setup, that can be restored. Or later, you'll know when an interrupts you, same idea. Okay? So the only thing is they didn't voluntarily call yield to do this. An interrupt calls that, triggers it, pushes the return address, but otherwise it's the same idea. Okay? So set up the SP, set the SP to the saved SP for the initial thread, and then finally do a return to this newly created thread ID. Okay? And that way, well, so basically you set up the stack and then restore those registers, finally followed by a return. Then return is the beginning of that function, which is main in this initial case. Does that make sense? So we've gone over this twice, once last time, and this is much more detailed step, okay? But you should know what's going on. And then thread yield, what does it have to do? Thread yield does 2 things. Thread yield first does a save state, then followed by a restore state. I already gave you the answer here. So that makes sense because whoever calls it saves the current context, right? And it has already a return address. Basically, by definition, when you resume back to where thread yield would return to, right? Except you don't return right away. Instead, you save its context, you switch to a different thread, then you return from thread yield after restoring its context. Okay? But if you only have one thread, what happens? Well, it saves a state and then does a whole bunch of things, select, oh, it's the same thread, so it restores. So it kind of does useless thing. You could do that, or you could just check. Do I have any other thread to switch to? No? Okay, then return right away. You could do that too. But this is just the general structure, okay? Assuming you have another thread. But it should work correctly either way. So even after that trouble of saving state and then restoring, it should be the same, right? Because you just copy things to a stack and then popping them back. So anyway, so for now, we hardwire a little scheduler, round robin scheduler. Everybody should know what round robin means. So you have like threads 1, 2, 3, 4, 0, 1, 2, 3. So if you have 4 threads, run thread 0. When it yields, run thread 1. When it yields, run thread 2. When it yields, run thread 3, and then go back, right, to thread 0. Everybody gets a turn to run. That's the simplest one. That's only one of many possible scheduling policies. So do that. That shouldn't be very hard to do, right? You should be all very comfortable looking at the bit map, and then check which bits are set, and then do some bit shifting, and then figure out where the next bit is if there's one, and then pick that, okay, and go and so forth. So that's why you actually need to keep a kind of the current ID for the current thread, and then also which threads are active. So you keep testing and then kind of move around, right? So there should be at least one thread. So this allows the loop to always terminate, okay? What happens if the last thread exits? Well, okay, that's kind of outside the scope of our project, but you could think of something reasonable. You could restart main or jump to some infinite loop. That's another way, okay? So at least we don't define that behavior, but you could certainly do some research and see how other threads packages would do it. Okay, thread exit for now, we don't do much, but if you really want to try something, okay, you could. Basically, you take the current bitmap and then find which one it is, and then clear it, and then do select the next one that's active and then return to it, or that's by a restore state, right? So, but strictly speaking, you have to do more than that, because if you remember POSIX API or other API, there's thread join and threads detach. Remember those, right? What does a join do? Join says, okay, the child thread or whoever thread exists, but don't clear its memory yet. I want it to stick around until I call a join on it. After join, then, okay, free up. Okay, detach just says, as soon as it exits, free it up. That's the difference. Okay, here we haven't even defined join and detach. So that's why this is just a placeholder for now. Okay, and so you should be very clear on what to do. If not, go back to your slides and actually read the comments very carefully. And do ask questions. We're here to help. I mean, there's the OS Q&A. I've seen questions up to week 3, and for some reason, no more questions. Which, please do ask more questions. I'm sure you have lots of questions. So. Yeah. Ask a TA or post a message if you don't know how to access this. You ask questions on ILMS, right? Or there should be a way to link to this. So from ILMS, what do we do? This is the ILMS website for this course. So which? Forum. This one here. Yeah, there we go. QA. Yeah. So you can add new discussion here, or you could do all sorts of things. Ask daily questions here. Ask questions related to course material. You could do these things. Okay. And yeah, and there you can do this. So do ask questions, because if you don't, we really don't know what you know and don't know. So yeah, there's a lot of detailed answers. TAs are very, very helpful. So certainly we're here to help. Okay, so a lot of these questions are from a couple weeks ago. Please ask newer questions. Okay. Don't be shy. And really, you gotta go through this to really understand OS. Otherwise, you're just reading things and then don't have a concrete idea. Okay. All right. So I think that's it for today. And also, we reserve the rights to give quizzes. And the quiz questions are gonna come right out of this kind of thing. So. No sense memorizing these. You should see. I mean, this is really a check. Do you think you can explain any of this, right? And these are taken straight from the slides. Basically, I just turned this presentation slides into question form. Did you get it? Because it's very easy to miss 1 or 2 points by just looking at the slides when you review. So, yeah.
In the midterm, you are gonna ask concepts coming from the book. Slides, or just free of it related with the topics?
Think these questions in different forms. So, right, and specific questions on programming as well.
Because
yeah.
I was my main concern is that there is some like tricky questions about that, for example, the specific version of this operating system, like you told us in the slide, like Darwin, the architecture, the monolithic, specific historical related issues with the operating system. These kind of things
Okay.
is not related.
If it's, I'll take questions straight out of these review questions.